Okay, dear colleagues, let us start our seminar. Today our speaker is Viktor Mishnyakov from Nandita, who will continue the topic of previous seminar and tell us about superintegrability of matrix models. Okay, you are welcome.
Thank you. Thank you for having me. Indeed, I'll talk about matrix models, their superintegrability, and relation to so-called BPS algebras. So, yeah, basically, I'll kind of talk somewhere in between this diagram. I'll not describe this part, like the origin of the family of the so-called BPS algebras. Instead, I will focus on superintegrability and its relation, or rather, it's some kind of hidden symmetries that apparently are realized by a family of algebras that are now known by the name of BPS algebras. So let me first, before I outline the point of my talk, let me first start by introducing just a few concepts and notations. So when we talk about matrix models, we talk about taking some kind of integral over a space of matrices. Then we integrate some function, and the measure includes some kind of exponential of potential v of x. And usually, when we talk about matrix models, we tend to consider invariant quantities. So usually the potential that depends on the matrix also only depends on the traces of the matrix, and the functions that we integrate also depend only on the traces of the matrix. Now, when we talk about generic matrix models, we can integrate over very different kinds of matrices, Hermitian, unitary, orthogonal, others. And depending on that, the measure, this large dx here, will be different. In my talk, we'll be mostly talking about Hermitian integrals. Also, if we're talking about invariant integrals, we can pass to the integral over eigenvalues. Since everything depends only on traces, we can diagonalize our matrix and make this change of variables. And in the Hermitian case, this will produce us the following integrals. Now, these functions f are obviously symmetric functions of the eigenvalues of the matrix. We integrate over these eigenvalues. And here, there's an additional factor which comes out of basically it's a de Jacobian of this transformation, and it's the square of the Vandermonde determinant. So these are kind of the objects that we want to consider. So in this case, these are matrix models. Sometimes the object below are called eigenvalue integrals or eigenvalue models, because generically we will later consider deformations of this integral such that they already don't come from integration over matrices. Also, it's common to consider the following object, this sort of generating function of all invariant polynomials. So we put our potential here and then sum up all the traces with some parameters p, and obviously we treat these pk perturbatively, so we expand under the integral, and then we get a formal series that is the sort of generating function of all the expectation values of all the invariant polynomials of the matrix. So it is well known that matrix models appear in a variety of problems in physics, some of which I listed here. So nowadays, often matrix models are encountered as a result of supersymmetric localization in supersymmetric gauge theories. Also, it was kind of well known, and this subject became popularized because it allowed treatment of perturbative and actually non-perturbative string theory or quantum gravity. Then some lattice gauge theories. Lattice approach to gauge theories results in matrix models in statistical physics. These theories are known as this theory is known as theory of random matrices or random ensembles. Also, non-commutative gauge theory is related to matrix models. So there's a whole variety of problems where one kind of gains the intuitions and that supply us with different matrix models. And actually, matrix models are interesting kind of on their own because they're a sort of playground model for QFT. Obviously, a very simplified one. So they are kind of zero-dimensional path integrals, and by studying them just on their own, we can hope to learn something about zero-dimensional or just generic path integrals. So this is like the overall motivation. So now this is the plan of the talk. I will review the subject of superintegrability in matrix models. I'll try to explain what it is, try to demonstrate that it is a non-trivial phenomenon. Then I'll go to describe this W representation and how it leads to the discovery or description of some hidden symmetry algebras that kind of reflect this superintegrability phenomenon. And then I'll describe two types of applications of this concept. So one is going to be about some sort of commutative subalgebras in these symmetry algebras that come from matrix models. And the other one is the superintegrability of the Uglov model that was recently, that is described in a recently published paper. So let me go on to describe this superintegrability of matrix models. So it appears that sometimes in matrix models, expectation values of certain quantities can be computed exactly and explicitly. So there is this review 2 years ago that kind of goes over a bunch of models where such things happen. And often this phenomenon is realized in this kind of symbolic formula that an expectation value of a character is expressed via characters as well. But more generally, it is realized as the following statement. So it appears that we can find a special basis in the space of, well, either invariant polynomials of matrices or the symmetric functions of their eigenvalues. So such special basis that, well, first of all, its expectation values can be computed exactly. And moreover, it happens so that it is usually the case that the function that we integrate is the same function that appears in the answer, while it is evaluated at a special point. So it kind of looks like perhaps even kind of equivariant localization calculation, or maybe an exact mean field approach, but it is not yet clear what happens and how this phenomenon should be described invariantly. But I will provide a bunch of examples. And this is what is basically called the superintegrability of matrix models. I guess a less ambitious name would be just exact solvability of matrix models or exact solutions. But there are reasons to call it superintegrability as an analogy to the standard superintegrability in classical mechanics. So the simplest case is the Gaussian integral, but the matrix integral in that case. So we integrate over the space of Hermitian matrices n by n. And for the potential, or the trace for the potential, we choose minus trace x squared. and we integrate everything from minus infinity to plus infinity. And well, obviously in the Gaussian case, we can calculate things using simply Wick's theorem, but still for a generic combination of traces, the Wick's contractions, well, there are many contractions, it's hard to describe them invariantly. However, if we pass to a correct basis in the space of invariant polynomials, then the answer greatly simplifies. And the correct basis in this case are the Schur functions. And it appears that the answer, so if we integrate, take an expectation value of the Gaussian weight of Schur functions, then the answer is pretty simple. There are two ways to represent it. So first is this, where on the right-hand side, we see that we have a Schur function already evaluated at a special point. And here we have a very simple dependence on n, which comes in a sort of combinatoric way. Mainly, it is represented as a product over all boxes of a Young diagram. So the Schur function is labeled by partitions, and so partition R here. And in partitions, boxes of the partition have coordinates I and j, and we can take a product over this quantity over all boxes of the partition. This function j minus I is usually called the content of the corresponding box. And well, here's an example. So here are the I coordinates, they're horizontal, and the vertical are the j coordinates. So therefore, this Young diagram gives the following product here. So it's a very simple factorized dependence. And moreover, this quantity actually can be also represented as a special value of Schur functions, in particular as a ratio of Schur functions evaluated at these special points. So I probably have to comment on these special points. So when we consider Schur functions, well, there are kind of two ways to look at them. So one way is to think of those as symmetric functions of some variables, x, say, and the other is to rewrite them in the basis of power sums. So sums of xi to the k. So these pk variables will be power sums. And when we rewrite them as power sums, we can evaluate Schur functions at special values of power sums. So in particular here, to calculate this Schur quantity, this Schur function at point pk equals delta k2, we rewrite the Schur function in power sums, and then we put all power sums except for the second one to 0, and well, the second one to 1. And to express, it's quite simple to express Schur functions in power sums. Well, mainly most definitions, kind of, or technical definitions of Schur functions deal in the power sum basis from the beginning. So it's quite easy to calculate those. And for example, here in this numerator, we put all power sums equal to n, which actually in the sort of symmetric variables would mean that we take all the eigenvalues or equal to 1. So anyhow, so this is a nice explicit formula. However, I mean, it is a feature of Gaussian integration. Perhaps one could think that this is a coincidence, and well, there are many nice features of Gaussian integrals. However, it appears that this property holds for many different cases, so for many different potentials and many deformations that include non-Gaussian models, logarithmic or higher monomials, potentials with external matrices, or non-matrix deformations of the measure, such as the beta or QT deformation. So, for example, a natural kind of deformation in the theory of matrix models, and also in random matrix theory, and also in all the related subjects, is the so-called beta deformation, when instead of the square of the Vandermonde, we put Vandermonde to the power 2 beta. And well, so this deformation should be done already after we pass to the eigenvalues. So because for generic beta, this eigenvalue integral cannot be represented as a integral over matrices. So only for special values of beta, such as beta equals 1/2, 1, and 2, it can be represented as an as coming from an integration over orthogonal, well-symmetric, Hermitian, and symplectic matrices. So anyhow, it appears that in this beta deformed model, we can still find a proper basis for our expectation values. So if we try to do sure functions again, it won't work. It will give just very messy and well, completely intractable answers. However, it is quite well known that this beta deformation corresponds to substitution of sure polynomials with the so-called Jack polynomials, which are also symmetric functions, but now depend on beta. And indeed, if we integrate these Jack polynomials with this Gaussian weight with a beta deformed model, we get an explicit answer again, and in a very nice way, the answer gets deformed exactly. So the form stays exactly as it was. Instead, we just substitute sure functions with the Jack polynomials in each of these parts of the formula. And this ratio of Jack polynomials is also a factorized quantity now, which is also a product of boxes. However, now it also depends on beta. So this is a kind of beta deformed content of the box. And actually, this formula is really hard to prove. It appears to be hard to prove. At least we didn't know of any proof. It was like an experimental fact. And well, later we proved it with the indirect methods, which I will partially describe. Well, in part because already all the methods that work for, lots of methods that work for Hermitian integrals, which are unitary invariant, they don't work for this beta deformed model. Well, at least here we cannot use a Wick's theorem for generic beta. We have to kind of interpolate between integer beta. Well, we don't have any techniques related to like KP or total integrability, free fermions, or any of that stuff. So it appears to be hard to prove, and well, at least no direct proof is known. Anyhow, we don't have to stick to Gaussian potential. We can change the potential as well. So in particular, if for the potential we take logarithm, then well, exponent of logarithm will give us some polynomial expressions, and in particular, we will obtain these kind of integrals, and these integrals are well known under, I guess, the name of Cadell integrals. So, however, still they can be kind of rewritten in the form that would suit this general scheme. So again, we have an expectation value of Jack polynomial that is explicit and is expressed via a expression that contains Jack polynomials evaluated at special points. So now here we put pk equals to n, and here we put all power sums equal to this expression, and then in the denominator we put all power sums equal to that expression. And there are many more examples. However, I'll not go to describe all of those. Yeah, so another important point is that this beta deformation is not kind of only related to matrix models. It's beta is a consistent parameter among many subjects. So in this kind of statistical physics interpretation of matrix models, it corresponds to temperature. As I said, it interpolates between orthogonal Hermitian and symplectic ensembles. So in the relation of matrix models to CFT, to conformal theories, it corresponds to non-trivial central charge. Also so in the AGT dual parameters, it corresponds to equivariant parameters, and also it corresponds to a non-trivial coupling in the Calogero model for whom Jack polynomials are eigenfunctions of the Hamiltonian, and actually more. So this the substitution of Schur functions by Jack polynomials and beta deformation is not kind of arbitrary. This this deformation and all these quantities, all these objects are kind of related to many other subjects. So another example, which is important, which I will want to kind of extend further, are the non-Gaussian models. So if we take a sort of Gaussian potential, just a potential of a higher degree monomial, then we could also ask if this model has the superintegrability property. But now we have to be careful because when we integrate higher degree monomials, we have to actually choose the correct integration contour such that the integral will be divergent at least. And it's known that, well, for the cubic potential, there are at least two such independent contours or classes of contours. So one have to specify this also in the case of matrix models. So to do this, one has to pass to eigenvalues. So in the eigenvalue integral, we just simply have an n-fold integral. And then for each of the n integrals, we can choose one of the s-1 independent contours such that the integral would converge. And it is not known whether this model has the superintegrability in the generic case. So the generic case is when each eigenvalue is integrated over its own contour. However, the case that is known is when all eigenvalues are integrated over the same contour. So this contour CSA here. So we take CSA to the n, so we integrate all eigenvalues all over the same contour. And this contour is chosen in the following way. So it's a specific representative such that it is simple to integrate over. So we take the rays from 0 to a complex infinity, and we sum up this rays with different coefficients. And these coefficients, they depend on so depending on the choice of these coefficients here, which are roots of unity, we get different contours. And so this variable a, it labels different choices of contours. So a also runs from 0 to s-1. And in particular, in the cubic model, we get the following picture. So we have this 3 rays from 0 to various complex infinities, and we take a sum of these rays. And when we take the sum, we also multiply this ray by this quantity and this ray by this quantity. And so depending on the value of a, we will have different contours. And in fact, a equals 0 corresponds to a contour that has a boundary. So if we want contours that are, well, closed contours that don't have a boundary, then a runs from 1 to s-1. And so in the cubic case, exactly, we get exactly 2 independent contours. So it is known by these people here that for such choice of integration contours, the model is super integrable, and one can write an explicit answer for expectation values of Schur polynomials. And well, this is actually kind of exciting because this is a non-Gaussian integral, and well, obviously non-Gaussian integrals are known to be kind of hard to calculate. Well, of course, in this case, it is a simple representative of non-Gaussian integrals, but nevertheless, in this kind of balance, it appears that one can write explicit answers. And moreover, they are nice kind of generalizations of the Gaussian answer. So here we again have this Schur function at special points, at a special points, which is now simply delta ks instead of delta k2. And here we again have a combinatoric factor, which is a product of this n-dependent contents. However, now it is a little more complicated since, well, so now these factors enter with this double bracket notation, and this double bracket notation, so here I tried to explain it. It says that, so if you have a small n double bracket s comma a, it's n if this n modulo s is equal to a, and otherwise it's 1. And clearly this, so this means that the values here will also depend on the value of n, or rather on the value of n modulo a, or modulo s, sorry. And in particular, for the, so if you want to have averages which are normalized, such meaning that the expectation value of 1 of just the trivial Schur function is non-zero, then we are forced to choose n equals either 0 or a modulo s. And well, depending on this choice, this answers also kind of vary. So just to illustrate this, if we choose n equals 0 modulo 3, and then consider these two factors here for just, well, a random Young diagram, then so this particular product over this Young diagram would correspond to this expression here, and the colored boxes are actually the ones for which these quantities n plus j minus a well, are equal to this a modulo s. So the cases when this bracket is non-trivial, so when it's not identity. So for this Young diagram, we have this, and here we have the double bracket 3, 1, and then we have the colored boxes are now different, and we have a different expression here. So anyhow, even with this more complicated structure, we have explicit answer, which is nice. However, what was not known before is if there is a beta deformation of this non-Gaussian superintegrability. So one may wonder if we have this beta deformed we have the beta deformed Gaussian model, and we also have other beta deformed models. Perhaps we should have a beta deformed non-Gaussian, well, monomial, cubic, and so on models. But it appears to be not that simple. So we want a beta deformation of this formula, and the first guess is, of course, to substitute everything with Jack polynomials, as we did in the Gaussian case. However, it appears to not work. So if we just take the Vandermonde determinant and substitute it with a Vandermonde to the power 2 beta, and we'll keep the contours the same because, well, the x variables, nothing happens to them. But then we take the expectation values of Jack polynomials instead, and we get a complete mess. I mean, so the answers are, well, they're not factorized, and you really cannot obtain any kind of general answer, because actually also in these cases, the calculations, if one wants to do like straightforward calculations, say plug it into Mathematica and just calculate the integrals explicitly, it gets really complicated because, well, we have to do it at fixed n and at fixed beta each time, so we have to interpolate in these two parameters, and as soon as we increase n, the complexity of calculations becomes large. And if our expression is like a 5-degree polynomial in n, then to interpolate we need many points, and, well, I mean, it gets really complicated, quite hard. So not only we cannot obtain any answers for like large representations here, even for the simple cases, the answers are not nice, and then they're not factorized, and, well, there's no apparent general expression. And so the problem is that, well, there clearly is a problem of that. And the problem is that we are doing an uneducated guess. So we're kind of just thinking that perhaps this Jack polynomials work in the same way as in the standard Gaussian case. but we need to do an educated guess. And for that, we need some kind of symmetry argument. And well, so the symmetry argument is what I want to describe next. So, but first I want to describe what the symmetry is. And actually, the symmetry is also what allowed to prove the superintegrability of the standard Gaussian beta different model. And well, one can kind of trying to put a label on it. One can say that the symmetry is not internal for the matrix, so it's not a symmetry of the matrix. So it's not like an extension of the unitary symmetry of the Hermitian matrix model. It's a kind of symmetry of the moduli space, meaning that so to realize the symmetry, we want to look at the deformed partition function. So the partition function is defined by a maximal kind of set of operators. Well, I just kind of schematically write it here in QFT terms. So in QFT, we would include all possible operators here. Obviously, we don't need this generality. In matrix models, it is basically the expression that I showed before. So we kind of just include all the traces, which is basically a basis for all operators in the model. And so the symmetry is going to be realized in terms of these PK variables. So it's the parameters that control these deformations. And if you want to make relate this to the previous discussion about characters and so on, if we treat these parameters P perturbatively, which we usually do in matrix models, we expand this into a series, and using the so-called Cauchy formula, we obtain actually that this partition function is given by a sum of it's a pair of Schur polynomials. One depends on these external P parameters, and one depends on the traces, and the one that depends on the traces we integrate on. And so basically, this partition function of matrix model is expanded into series where the coefficients of Schur functions are expectation values of Schur functions. So if the model is superintegrable, we'll have some nice expressions here. And so this hidden symmetry of matrix models, it acts on the PK parameters, as I said, and its main realization, as it appears, the main way it appears in the models is through this W representation, where one can represent this whole generating function as an exponent of some operator, differential operator in variables P, which so it depends on P and the derivatives over P, acting on identity. And this W operator is usually kind of simpler than the whole partition function itself. So it's not like we're taking just a logarithm of partition function, but this W operator is usually is explicitly known operator, and we act with it on a very simple function, on just an identity. And this operator, it doesn't only have differentiations over P, so it has also multiplication by P, so it acts non-trivially on this identity. And when we expand this exponent, we act many times, and we represent the whole series, the expansion into Schur functions. So it was initially noticed in these two papers, basically at the same time, that this W representation can be used to prove the superintegrability in the beta deformed Gaussian model. And actually, in the Gaussian case, this W representation can be derived explicitly just from the matrix model using the so-called Virasoro constraints. I'm not going to describe that procedure, but anyhow, so this W representation can be just kind of explicitly, straightforwardly derived from the matrix model itself. But so to make relation to the superintegrability, let's look at the Gaussian example again. So we have the partition function, this time, this deformed partition function. It expands into Schur functions with the expectation values as coefficients. And if we plug in the superintegrability formula, we have this expression. So it's a sum of our partitions with a, well, so basically pair of Schur functions, one is evaluated, and also this combinatoric factor. And we also have this W representation. And of course, the question is how they are related. And since we have Schur functions here, perhaps a nice kind of, the first thought would be to check whether this W operator can explicitly reproduce this expansion just straightforwardly. And what we find is that this hidden symmetry basically is realized in the action of this W operator on Schur functions. And here we have that. So here we can look explicitly at an example. So this W operator is explicitly known. So here it's basically written in terms of this P variables. So all the sums here are from 1 to infinity. So it includes all these P variables. And as we can see, this operator is of degree 2 in the sense that if we prescribe to the P variable, so to PA, for example, we prescribe a grading A, then this operator has a definite, well-defined grading, which is 2. So here's, say, PA plus 2D over DPA. So this has degree minus A, and this has degree A plus 2. In total gives 2. And these terms obviously have degree 2, and these as well. So it means that if it acts on a function of a fixed degree in P variables, it will produce a function that is of degree, so that is of degree higher by 2. And Schur functions are actually also homogeneous in this degree. So this means that, this degree for Schur functions is controlled by the size of the partition that it depends on. So a Schur function of symmetric partitions of a partition of 2 boxes will be of this homogeneous degree 2. And this means that when this W operator acts on these Schur functions, it produces an expression which is some polynomial in this P variables, since it's of fixed degree. So it cannot be like an exponent or a series. It's of fixed degree. It's a polynomial of degree higher by 2 higher. And we can expand this polynomial into Schur functions again. And now it will be expanded into Schur functions that have 2 more boxes in the Young diagram, which we can think of as the W operator adding boxes to the partition. And well, basically this combinatorial structure is encoded in this formula. So here we have an expansion in SQ, which are now Schur functions of partitions with 2 more boxes. And then this coefficient here actually is related to the coefficient with which SQ appears in the expansion of a much simpler expression, which is just multiplication of the Schur function by this P2 variable. And we have this combinatoric factor, which of course reminds us this combinatoric factor here. And this is basically the key kind of hint that this is the right thing to do. And this combinatoric factor corresponds to basically the added boxes. So it's the partition Q without the partition R. And it is non-trivial actually that I think later show in more detail this formula. But it is non-trivial actually that this coefficient here vanishes in all cases when the partition Q, which is a bigger one, does not contain the partition R kind of as a part of it. So So it means that we cannot completely rearrange the partition. We can only add boxes on top of it. And I will perhaps demonstrate this a little later. So after we kind of so this is basically this data is not input in the matrix model. So we just discover that this happens, and we see that the structure emerges. And well, after studying a couple examples, it seems that it makes sense to study just the whole algebra of operators that have these nice actions on Schur functions. So they're kind of combinatoric. They add a bunch of boxes to the Schur functions and multiply them by some combinatoric coefficients. And well, it is kind of known that this algebra is nothing but the so-called W1 plus infinity algebra. So, and this realization that I showed here is just a bosonic Fock space representation. And indeed, in these representations, the operators from this algebra, they act explicitly on Schur functions in this combinatoric way. And well, since we want to kind of study this whole subject and application to matrix models, we need some very concrete statements. So we need kind of coordinate-dependent expressions. And for that, we developed a dictionary between operators in this algebra and superintegrability formulas. So in fact, one can just explicitly provide a dictionary that relates an operator that acts on a Schur function in a specific way. So it has this coefficient of the expansion of Pn times the Schur function here, and the product over some function of content over the added boxes. And if we have such structure, then we will immediately obtain a character expansion where this kind of coefficient is given by this expression here. And this expectation value of Schur function actually kind of does not need to be an expectation value of Schur function in any matrix model. So this is just kind of a notation here now, because, well, I mean, we don't know any matrix model that reproduces this formula for a generic function here. But just studying these operators, we can hook up any character expansion that we want. And in particular, we can choose any function g here as well. So, but the key kind of point that I'm trying to make is that for any function, almost any function g here and any n here, we have a dictionary that we can provide an explicit operator wn of g, which acts on Schur function in this way. And obviously, using this dictionary, we can also study the previous examples. We can return to the Gaussian matrix model, and we can kind of explicitly see that this reproduces. Importantly, and I will talk about that further, that these operators are nicely beta deformed. So in particular, again, studying examples, we see that given an operator here, there seems to always exist an operator, a similar operator that acts on Jack polynomials instead, in a very similar manner. Well, except for all components are kind of beta deformed, so there are Jack polynomials here, and the content product is also beta deformed. So I should have written here some kind of subscript or superscript beta. So it's a different operator that acts on Jack polynomials. But the point is that kind of for any representative here, we can think of a beta deformed analog. Yeah, and I think this, I guess I should have presented this a few slides before. But anyway, so just to finish this discussion about this combinatoric action on Schur polynomials. So here, if we take for this g function, we take n plus x. So in terms of the content, it's going to be n plus j minus a, which is j minus I, which is exactly what we need for the Gaussian model. Then we have the following operator here. So here I explicitly have written out all the combinatoric structures that are possible in this Schur polynomial case. So as we see, if we take this partition 3, 2, then the result that we get, and I of course omitted the coefficients here, so this is just kind of the partition structure of the right-hand side, is given by a sum of 3 partitions with 2 types of kind of double box structures added to it. So here we have 2 horizontal parts and one, and we have one way to add a vertical part. So as we see, there are no partitions on the right-hand side that, so we don't have a partition which is a completely anti-symmetric. So we don't have a one column partition because it doesn't, well, from a combinatoric standpoint, it doesn't fit into this, the initial partition doesn't fit into it. And this is basically the structure of how this operators act. And in the beta deform case, and actually the beta deform Gaussian model, will have a very similar structure, but with Schur polynomials substituted with Jack polynomials. So yeah, as I was saying, at least for Schur polynomials, we know how to, well, firstly, we know how to, how given a W operator, how to act on Schur functions with it, which is, I mean, this is straightforward. If we have the operator, we can just act. And then we also know how to reverse engineer the operators from these functions G and from the number N. We have an explicit construction for that. I want to briefly describe it, but I want to be very brief because I am running out of time. So the idea is basically, and it was, I guess, covered in the, somewhat covered in the previous talk. The idea is to construct it from very simple components. So basically what what we need is this operator W0, which is also known as the cut and join operator in this notation, and the simple operator which we call E0, which is just multiplication by P1. And as soon as we have those, we can construct lots of other operators. So this W0, as we can see, it is of degree 0, so it acts diagonally on Schur functions. And then we just construct iterating commutators. So we construct this EM as M commutators with E0, and then we construct this so-called HKM as these iterated commutators of EM plus 1 with EM. So I'm not going to go deep into describing the how this works. So here are just the examples of these operators. So these are of degree 1, but they are of different spin, so to say. So they have so this has the maximal number of kind of p variables that appear. Here's 2 and here's 3. So there are a few claims to make about these operators, and from the discussion that I had before, the important part is that now these operators, they explicitly act on Schur functions in this manner. So at least for any kind of polynomial function in this content, we can just explicitly give a construction for any given operator with any given kind of action on Schur function that we want. We immediately have it from this iterated commutator construction, and in particular for the Gaussian case, this is we will have the operator H12. And this action on Schur functions, it immediately follows from this iterated construction. And also what is another interesting feature is that for a fixed M, these operators with different Ks, they commute. This actually means that we can construct very general families of like partition functions. So we can take these HKM for a fixed M, but with different K, sum them up with auxiliary parameters P bar. And then we can exponentiate those since they commute. So there's no problem with exponentiating. And then we'll have these kind of character expansions of rather generic form. So from the point of view of total integrability, which is relevant for, of course, only for the Schur function case, we basically have explicitly described the W operators that are responsible for the so-called hypergeometric tau functions. And we can actually speculate that this commutativity of this family of operators is kind of the hidden integrability behind superintegrability. And as I said, these partition functions don't necessarily correspond to any matrix model. However, actually, well, not for the whole family above, but at least for m equals 1, one can, and generic p bar, one can construct a matrix model representation for it. So as I said, one can do beta deformation very explicitly without knowing anything kind of about the algebra. Basically, the construction is very simply deformed. We input beta in the coefficients here, and then everything follows just in the same way. We have this iterated commutators, and they act on Jack polynomials. So in particular, we get this Gaussian case, the Gaussian beta deformed case. And actually, this is how we prove the beta deformed superintegrability of the Gaussian Hermitian matrix model. So as I said, in the model itself, we can derive this operator from the matrix model, but after we derive it, we can prove that it acts on Schur functions in that way by using this construction here. And finally, in that way, you would prove this beta deformed superintegrability. So after we kind of look closely what is the algebra of the operators that we obtained, it is clear that the algebra obtained is nothing but the affine GL1 hat Yangian. It is a more complicated algebra. Well, it's not a Lie algebra anymore, but so basically the way we obtain it is a very explicit construction from a very simple set of generators, and then we just construct generic operators in this algebra and by iterated commutators, and also kind of it is simpler because we use a very specific representation of this algebra. And actually, in the notations, in the Yangian notations, this W0 is nothing but by the psi3 operator, and the En are also called En, usually in the papers related to affine Yangian. And what is nice is that, as I said, here we obtain a set of, I don't know if I wrote it. Yeah, right. So here we obtain these operators, and for just as for the undeformed case, for a fixed m and different k, these operators commute, and so in that way we kind of obtained some series of commutative subalgebras in this affine Yangian, and actually, since we have this construction here, we can actually prove that these operators commute without referring to any specific representation, so without referring to this explicit representation in this p variables. So we just need to use the generators and relations of the algebra. So it means that obviously that these are commutative subalgebras in any representation. And interestingly enough, one can ask if there are any integrable systems that are related to these subalgebras. And well, it was first studied in this paper, and then also in some of our other papers together. So it is known that if we have to do the following: we rewrite all of the operators instead of the p variables in terms of this lambda I variables, which are also just kind of well, these are the symmetric function variables. So in that case, if we do this for this W0 operator, we obtain nothing but the trigonometric algebra operator, where, as I said, beta minus 1 is, well, the coupling is proportional to beta minus 1. And so beta deformation is important here because at beta equals 1, we just get the free model. But interestingly enough, if we consider if we consider this H families of operators, then this H1 2, which is actually relevant for the beta different model, appears to be the rational coalgebra system. And well, operators with m equals 1 and k equals, well, other k are just the higher Hamiltonians of the rational coalgebra. And for higher m, well, we basically obtain kind of new integrable systems that can be studied. Well, some study on it is given in this paper. So yeah, I think I'm running out of time, but well, yeah. So the conclusion, basically the intermediate conclusion is that the hidden symmetry of this matrix models is given by these algebras, which for the Schur case, the undeformed case, is the W1 plus infinity algebra, and in the beta deformed case is it's the deformation of this algebra, which is the Yangian, the affine Yangian. So I think I have 5 minutes. I don't want to kind of go over time. So let me just kind of state the result briefly without going to details. So we can also use this idea, all the ideas, to construct deformations of known matrix models. So basically, since we know how to reverse engineer from, as I said, from any function g and then an operator from this W infinity algebra, we can do the same for the non-Gaussian model. But in that case, these functions, which kind of depend on the modular, on the residue of this number modular s, they appear to be, well, if we kind of rewrite them in an analytic form, they are already non-polynomial in X, and they're quite complicated. But if we look at them carefully, what we find is that these operators are actually kind of a limit of operators in a larger algebra, which is this quantum toroidal dim algebra. And basically, we find that they are values of these operators at when the quantum parameters q and t are equal to roots of unity. Yeah, so, and when we do that, we realize that the correct beta deformation should also be, well, not around the identity, not around qt equals 1, but qt equals the roots of unity. And therefore, basically, we kind of figure out that, so this is the correct kind of limit that we should take. And it is quite well known how to take this limit. So in particular, one can obtain this so-called Uglov measure here. So this is the substitute of the Vandermonde determinant. And also one can obtain the substitute of Jack polynomials, which are limit of McDonald polynomials when this kind of root of, well, the root of unity limit of McDonald polynomials. And so these are also some symmetric functions. And well, for r equals 1, so which is the kind of trivial root, basically the identity itself, it reduces to Jack polynomial. So here I have an example. So this guy is actually the Jack polynomial, and this guy is the first kind of non-trivial Uglov polynomial. Yeah, so is in this limit, the polynomials we obtain are called Uglov polynomials, since they were first considered by Uglov. And actually, in that case, they were related to eigenfunctions of the spin coalgebra system. And there are many other subjects. As for the Jack polynomials, there are many other subjects where these Uglov polynomials appear. And in particular, it seems like these Uglov polynomials are the analog. So as the Jack polynomials are vectors in representation of the affine Yangian of GL1, these Uglov polynomials seem to be vectors and representations of affine Yangian of GLR. And yeah, so basically combining all of that, we can obtain a beta deformation of the superintegrability of the non-Gaussian monomial model. So here's it in somewhat condensed notation. So this is the Uglov determinant that I wrote before, which is quite a complicated guy, which is certainly not simply the Vandermonde to the power 2 beta. But the nice feature is that everything else gets deformed in the way that we expect. So an expectation value of Uglov polynomial is expressed again as a value of Uglov polynomial with these combinatoric factors also beta deformed in a proper way. So the point is that we obtained this we obtained this deformation by looking at the symmetry. So we didn't know how to do it explicitly. However, after studying the symmetry algebra and gaining lots of intuition about it, we were able to deduce what is the correct deformation of these operators actually, and by doing that, we also obtain what is the correct deformation of the model. So we find the special functions that should be superintegrable, and we find the measure. And of course, there are a few comments to make here, but since I'm already over time, I'm just going to skip that. Yeah, so basically the kind of conclusion that we have now is that the hidden symmetry of superintegrability is given by operators, by algebras of operators that act in a nice way on partitions. And well, nowadays, such algebras are studied under the name of BPS algebras. And well, for matrix models, for now, at least the following four kind of algebras were realized. And so here are the cases that I have presented. And also, I didn't really talk about the QT models because they are not kind of so much studied yet. So there are things that are not understood in the QT matrix models. And well, there are actually some other examples which I didn't list here, but so some other algebras and some other models. And so the general kind of philosophy here is that, as I described, some questions coming from matrix models or kind of some constructions that are imposed from matrix model can lead to interesting conclusions about these algebras. So as I kind of briefly demonstrated, we can obtain infinite families of commutative subalgebras and construct integrable systems from them. On the other hand, intuition from these algebras, so symmetry arguments, can lead to new exact solutions of matrix models. So this is the subject. These two subjects are interrelated. Well, and obviously there are many more further questions. So just to list a few, apart from all the technical ones related to these algebras, to all these operators and so on, there is, of course, a huge room for extension to matrix models, to tensor models, and this work is already in progress in some cases. Also, models with external matrices and other ensembles, eigenvalue ensembles. Also, it is interesting since kind of we see that all of these kind of structures are algebraic. It's interesting to formulate this W representation, this exponent of a W operator acting in identity in a purely algebraic way without any reference to matrix models or any representation for that matter, simply in terms of the algebras that I described. And of course, it is always useful to think about what we learn about path integrals from all this study of matrix models. Yeah, thank you, and sorry for going a little over time.
Okay, thank you for your talk. Any questions?
McDonald polynomials. I just wonder about relations between McDonald polynomials and Uglov polynomials.
Yeah, I can repeat that. So basically, so McDonald polynomials, they depend on two parameters, Q and T, right? So we plug this Q and T to be these. So omega R is a root of unity. Well, the rth root somewhere, I think I have, yeah. So I have the omega S here. So it's 2 pi I over S or 2 pi I over R here. Sorry, yeah. So 2 pi I over R here. And so we take omega R U for the q variable, and for the t variable, we take omega r u to the beta. So we introduce a beta parameter in this way, and we take u equals to, and we take the limit u equals to 1. So apparently this limit exists. It is I guess it's a non-trivial statement for Macdonald polynomial, but this limit exists. It's well defined. Obviously, you should worry about the proper normalization of Macdonald polynomials, but then you get some non-trivial symmetric functions, which are called Uglov polynomials. And yeah, so and then obviously these polynomials depend on R. So depend for each root of unity, you get different polynomials.
So maybe similar question. So you have this particular specialization for Q and T, and do you believe that you have superintegrability in more general case? Maybe not for general McDonald's, but like for qubit packers, for example.
Well, I would think that generally it should be that I want to be careful about the kind of status of the statement, but it is somewhat known that so superintegrability for generic Macdonald polynomials is also kind of known, but now we should specify which model we're talking about. So there is a QT analog of a Gaussian matrix model. And then in that case, we have superintegrability of Macdonald polynomials. It's not proved yet, but at least you can see it from calculations that expectation values of Macdonald polynomials are given by Macdonald polynomials at special points. So, but this is for a QT Gaussian model. So, for example, for a QT analog of a non-Gaussian model, this is not known.
Maybe another short question. We've met this Uglov polynomials for R equals 2. Do you know if it is, so for beta we have these special values like 1/2, 1 and 2. For R, is this like R equals 2, for example, somehow specific? Do you have some additional structure in this case?
Yeah, so there is an interesting, so yeah, I don't know, perhaps I didn't list maybe all of the, but anyhow, right. So I don't know, I think I have an extra slide here. No, anyway, so if we look at this, yeah, right. So if you look at this model here, then actually we see that the naive, like the Gaussian kind of case of this model is actually given by S equal 2. So this means that we will take the Uglov polynomials for R, well, R equal S equal 2. So this is this kind of the second root of unity. However, before I was describing that for the Gaussian model, superintegrability is given by Jack polynomials, which are Uglov polynomials for R equals 1, also for the trivial root of unity. And actually, it appears that for this for this Gaussian case, there are two superintegrable formulas of superintegrability. There are two exactly solvable models. So one is with R equals 2, which corresponds to the R equals 2 Uglov polynomial and the R equals 2 measure, and the other is the other is with a Gaussian potential, but with R equals 1 instead. So Jack polynomials and the standard beta deformed Vandermonde. So in that case, in that kind of meaning, yes, the R equals 2 is somewhat special. But if you want to ask about its relation to like any specific ensembles, then well, from here at least it doesn't. I mean, because even for R equals 2, we have this non-trivial factor where we have these eigenvalues raised to power 2, and well, such expressions don't usually appear from any kind of matrix integration. So at least they're not in any simple way related to any explicit matrix integral.
Okay, thanks a lot.
Okay, maybe one more question. In the name of the talk, you call the algebras BPS algebras. And could you explain why?
Yeah, well, from what I described, it's I mean, so I didn't make any reference to anything. So these algebras appear in many contexts. In particular, in counting of BPS states, for example, but also in like they act on instant on modular spaces and so on. So this name comes from there. Like before I kind of realized that this is the proper name, I would just call them algebras of operators that act nicely on partitions. But in the literature, these algebras are known as BPS algebras. So,
Okay.
but these partitions represent like BPS states and so on. And these algebras act on these BPS states.
Yeah, and in a classical mechanical superintegrability, the usual case that you have not only the commutative algebra, but also a non-commutative one, which is larger, but commutes with this commutative part. Do you have some structure like this here? So probably
Yeah, so,
yes.
So we kind of, yeah, like there are kind of various ways to try to justify this name. So, but okay, let me just generally explain kind of the intuition, because so if we just look at the undeformed matrix models, the one for Schur polynomials, for Hermitian matrix ensembles, then we know that the partition functions of these models, well, these P time-dependent partition functions, are tau functions of Todo or KP hierarchy. So there is a kind of integrability behind it just straight away. However, they are tau functions for any so actually the fact that they are tau functions don't really depend on the measure of the model. It just cares about the Vandermonde being not deformed. So and it means that this kind of integrability doesn't explain the structure of averages of Schur functions. So there are many other kind of matrix models which can be also tau functions of hierarchy, and so it doesn't fix the structure of the expectation values. So in that sense, there should be an additional kind of symmetry, which I was trying to describe in this talk. But right, from the perspective of classical mechanics, there should be some relation between the two kind of symmetries, but kind of we don't really find it here. Also, another kind of way to think about is that for this KP integrability, so to fix the values of expectation, so fix the values of expectation values of Schur functions, you have to complement this standard integrability by so-called Virasoro constraints. This is also another way to kind of do it. And Virasoro constraints, they're kind of analog of equations of motion for classical mechanics, but in matrix models. So interestingly enough, when we take the Virasoro constraints and we plug in the KP integrability into it, we get, instead of any like differential equations, we get simply algebraic combinatoric relations, which can be exactly solved after that. So this is kind of another analog of what might happen in classical mechanics. So, but otherwise, I don't think
that differential, yeah.
Sorry.
Algebraic equations instead of differential ones.
Yeah, kind of. Yeah. So, but so I don't think we, at least for now, we can make it more like more precise. So as you said, to like have actually like a number of integrals, some of which can be used and so on. But yeah. So, but as I said, this is an analogy which I think is justified, but still to some extent an analogy.
Yeah, okay, thank you. Becomes more clear. Any other questions? Maybe from Zoom? Okay, if not, let's send the speaker again.
Okay, thank you.